Yeah, thanks, Tian, for presenting. Let's get started. So greetings, everyone. Thanks for having us, and really excited to be representing Etsy for the very first time in the Feature Summit. So our team, as I mentioned before, basically work on both batch and streaming feature systems. And today we'll be focusing on Rivulet, which is our real-time feature store. So let's look at the agenda. So we'll start with the overview of the system scale and how we handle different types of features at Etsy. Then we'll dive into the Rivulet architecture and explain how we support each step of the feature workflow. And lastly, we'll discuss a little bit about some challenges with our current system and some ideas of addressing them. So let's begin with looking at the scale of our system. So as you may already know, Etsy is a global marketplace for unique and creative goods that connects our community of over 6 million makers, artisans, and creative entrepreneurs to over 90 million of buyers looking for something special. So every purchase on Etsy comes from a real person, and the Etsy's machine learning teams are constantly working to create a better shopping experience that drives more sales to our small businesses on our platform. To support the Etsy scale, our feature retrieval service handles about 200,000 requests per second for batch features and around 160,000 requests per second for our real-time features. The average P99 retrieval latency is about 50 milliseconds. The real-time time series features are available within about half a second of ingestion latency since the source events were fired, and the numeric features are usually delayed by about 15 seconds. So let's look at what kinds of features we support today. So we categorize these ML features into three main types: batch features, real-time fact features, and real-time aggregated features. So batch features are ingested with a scheduled batch pipeline, with both types of real-time features are ingested with the streaming pipeline from the input Kafka stream. So since real-time fact features do not require any runtime aggregation, and thus it does not require tracking timestamp information in the database, we store them with the same schema as batch features. So all the features for each entity ID are on the single big table row, but in different column families and have different column qualifiers. So on the other side, the real-time aggregated features use simple key value schema. Each key is composed of feature name, version, entity ID, timestamp, and a hash of the entity ID prefix, which we use to avoid big table hotspot issues. Speaking about the real-time aggregated features, we support three different types of those. So there are like numeric or count features, which compute things like sum, max, average, and count over a specific time period that we call the aggregation window. Secondly, the time series feature compute a time series of elements for a given feature key. And then heap features are used to represent popular or trending elements for a given key. So now we'll walk through examples. We'll see how each type of aggregated real-time feature is computed, stored, and retrieved. So let's talk about count features first. So let's say we want to build a model to find the most relevant listings for a search query. We may use a real-time count feature that tracks each listing's total view counts in the past 24 hours. So all real-time feature data comes from raw beacon stream. Beacons at Etsy's data infrastructure refers to events or signals that are logged and processed through various pipelines for analysis and tracking. So here's a simplified version of some examples of beacons. From the raw source stream, the streaming ingestion job filters the relevant events, such as view listing beacons with valid listing ID fields to compute the feature values. Then comes the most important transform in the feature ingestion pipeline, which is pre-aggregation step. So for any count or numeric feature, the feature creators can define a pre-aggregation bin size, which is smaller than the feature's total aggregation window. This pre-aggregation bin is used to reduce the number of rows needed for the big table scans and runtime aggregation in the feature service, and further reduces the overall feature retrieval latency. So in this example, if we set an hourly bin, the pipeline rounds the timestamp of each incoming beacon down to the nearest hour and count the beacons per listing for each bin. The pipeline then retrieves the historic values for the bin from Bigtable, merges the count, and updates them back. Now at the retrieval side, when the service sends a feature request for the listing view count feature for let's say a given listing ID L1 over 24 hours window, the feature service dynamically scans through the Bigtable rows, fetches the rows which basically contained within the lookup time, and then aggregates the time series values to return the final feature value. So now let's look at the other kind of aggregated real-time feature, which is time series. So in addition to the general listing popularity feature, we may also want to understand the interest of the user who submitted the query, such as the 50 most recent listing IDs viewed by a user. How do we compute that? So from the same view listing beacon, we will now filter all the records that contain both listing IDs and user ID fields. Then for time series features, we don't need to pre-aggregate values. Instead, we'll store each point in the Bigtable with its raw timestamp. Since we set a truncation rule at the request time to return only the most recent 50 listing IDs, the feature service platform basically will perform a streaming scan on all the rows for the feature and for that specified entity ID, the listing ID, and then it retrieves the values until either all the relevant rows have been collected or the listing ID count reaches 50. So with that, let's look into how heaps work today. So heap features at Etsy are a special type of features usually used to determine popular or trending items. It is generally calculated based on the richer count feature that tracks the additional information like the listing ID in this case. It gets stored in a heap store with a special key format designed to ensure the correct ordering during the feature retrieval. Let's take the top purchased listing ID in the past 4 hours as an example. So here you see the pipeline first calculates the purchase count for each listing ID within the past 4 hours, like any other count feature, and then return the count value along with the listing ID as additional context for the heap entry computation. The pipeline then constructs the Bigtable key for the new count value with the feature name, version, heap key, and encoded count string and the item ID. In this example, the heap key is the reserved word all, since we want to compute the total purchase count across Etsy. The item ID is the listing ID, since the feature asks for the top purchase listing IDs. To make sure higher counts are ranked at the top, we encode each positive number with a 9's complement. So for 10, the 9's complement will be 89, and then prefix the number with a string, which is the length indicator. So this length encoding takes advantage of the lowercase alphabet, so we can support up to 26 digits of numbers. So for 10, since the length is 2, the length encoding will be Y. So before pushing the new heap entries in the Bigtable, we pop the existing ones out, aggregate them, and then modify and then store them back again. Now, during the retrieval, the feature service would return the listing IDs and the purchase counts in decreasing order. Similar to the time series feature, the feature creator can specify the truncation options for example, up to like 50 listings or so. With that, I'll pass it over to Tian, who talk about the overall Rivulet architecture and the feature workflow.
Thanks, Prachi. Now that we have covered how each type of real-time feature is processed and retrieved, let's zoom out and discuss the overall architecture of Rivulet and how it supports our feature workflow. So Rivulet was built and launched in 2019 as SE's first centralized feature store. It was adopted quickly by most of the internal ML teams, like ads, recommendations, search, etc. It was built for the cloud environment during SE's general migration from data center to cloud. And since the upstream data infra migration plan was not finalized by the time, and there was even no clear ML use case of streaming features, Rivulet was designed with resilience to uncertainties in mind and was only targeting a small volume of online requests from non-ML systems. But however, today, the majority of those requests come from ML model inference, so they're often in large batches of many features. So we're continuously optimizing the system to handle the new challenges. Here is an overview of Rivulet's system architecture. Our ingestion pipeline consumes the source event stream and writes the intermediate values to Bigtable after pre-aggregation. There's a daily snapshot job that dumps the Bigtable rows to a GCS bucket for a time machine to compute training data. A feature service retrieves and aggregates rows from Bigtable to compute the final feature values for the online services. When features with like a longer aggregation window, like 30 days or more, are created, we really need to backfill the data from historical events to generate accurate feature values sooner. The backfill job reads from the GCS copy of the event data, computes intermediate representation, and adds to both the production Bigtable and the corresponding GCS snapshots. The feature definition are referenced to determine the computation logics in all of those ingestion pipeline, backfill jobs, feature service, and time machine components. Supported by Rivulet, our feature workflow usually starts with researchers exploring existing features and raw event data. When a promising feature is identified, they define it in the dev environment, backfill for training data generation. And after it's proven to be effective in offline experimentations, we move the feature to production and load the backfill data into the production Bigtable for serving. Feature exploration is usually done with either like spot checking using our hydrology tool or value analysis using the using the BigQuery on raw event data. The hydrology tool calls the SE Web API under the hood to translate the listing IDs to listing images for convenience to our researchers and data scientists. For feature registration, like all the Rivulet features are defined declaratively in Scala code, as shown on the left of this slide. It requires some specialized knowledge to engage with, so to make feature creation easier, we have started initial prototyping work with a YAML-based feature registry, whose configs are text-based and easier for feature producers to interact with. Just a note that it is still under active design discussion, so the schema is not final yet. Like in this very initial draft version, we have removed the event filtering logics for upstream applications to handle. When a new feature with a larger aggregation window gets introduced, like I mentioned, we run the backfill job to fill the missing range. With the feature of the listing view count for the past 30 days as example, if we create the feature on October 12th at 9 a.m. UTC, and we plan to start serving this feature in 3 days like today's morning, none of the feature data would have the full 30-day view of historical events. And thus we need to backfill the rows between September 15 and October 12. Oh, sorry. For either an experimental model or production model, training data can be collected in two ways. The first one is by logging the production request, which is highlighted in yellow color in the diagram. It is preferred for models that are updated very often and cannot wait more than 1 day for training data. The other approach is by running the batch job that computes the feature values with the Bigtable snapshots. The second approach can generate training data, include the new feature values for requests even before the new feature has been productionized. So ML teams can get any time range of training data as soon as the feature is created. Regarding feature service, the current feature service is built with a simple REST-like framework. The two most important APIs are like single feature GET request and batch feature POST request. A single GET request requires a feature name, version, entity ID as the feature key. It will return a JSON object with the feature name, version, key, and feature value in it. Feature consumers can also add additional truncation rules or accumulator customizations in the request. The truncation options are like limit the max number of results to return or restrict the time range to slice time series rows from Bigtable. Accumulators provide like additional post-processing options on the results. For example, we may want to get the deduplicated list of buyers' recently viewed listings to help them continue a shopping journey that they might not have finished yet. Or in some other cases, we could make recommendations based on buyers' viewed listings only in their most recent visit session to help them find a desired item more efficiently. Like if we implement all those logics in feature consumers' own client, since the Rivulet feature service communicates with Bigtable through a fixed bound scan query, it may overfetch more results that they need to, or make multiple round trips to sequentially obtain the desired number of unique records. In this demonstrated example, it first fetches the most recent 5 records, does deduplication in its own client, sends another request to fetch remaining 1 listing ID. But with the dedupe accumulator, we can perform a streaming scan following the observer pattern. So the streaming scan has a predetermined start, and Bigtable will stream the rows back to feature service one by one for consumption. This dedupe accumulator only accumulates records that it has not seen before and will return the values once it reaches a terminating condition. And in this case, the terminating condition would be 5 unique listing IDs have been found. The accumulators are like essentially useful to avoid unnecessary requests and data transmitted, and thus further reduce end-to-end latency. The batch post request asks for similar information as a GET request, but allows sending a list of feature requests together. Okay, despite all the successes, like any other system, Rivulet faces challenges, and we're actively working on optimizing the system using the knowledge we have collected over the years. So for example, like I mentioned, feature creation via Scala code can be cumbersome for feature producers. So we're developing a more user-friendly solution with a text-based feature registry, plus some automatic validation deployment to smooth the process. We also aim to improve the API performance to better handle the growing volume of batch requests. Finally, like the redesign of the system can reduce the complexity of the legacy code and further reduce the team's maintenance burden going forward. That concludes our presentation. And thank you all for your time, and special thanks to our amazing team for their contributions.